All right, welcome to this explainer, everyone. Today, we are going on a highly focused, absolutely fascinating journey into the literal mechanics of ferromagnetic substances. We'll be using study materials from Physics Vidyapith to break down exactly how these incredibly powerful materials operate. We're going to move step by step from the tiniest microscopic pieces all the way up to the macro-level reactions we actually see and feel in the real world. So let's jump right in.
To kick things off, we really have to ask, why are some materials just so strongly magnetized? We've all felt it, right? That intense, sudden snap of a strong magnet pulling on a piece of metal. But what's actually happening under the hood to make that happen? Well, to truly grasp this, we've got to start our journey by zooming way into the atomic level. We literally have to look at the invisible building blocks of the material before we can even begin to understand that visible, macro-level pull in our hands.
Okay, let's dive into this. The foundational building block of ferromagnetism, the whole shebang, begins at the atomic level with these permanent magnetic dipole moments. And the culprit behind them? Unpaired electrons. Think of these unpaired electrons as, restless tiny engines inside the atom. Because they are unpaired, their individual magnetic contributions just aren't canceled out by a partner spinning the opposite way. It's that lack of a partner that leaves the atom itself with a permanent, built-in magnetic identity. That is the absolute starting point for everything we're about to see.
Now here's where it gets cool. These tiny, restless atoms don't just hang out by themselves, they actually form neighborhoods. In physics, we call these specific regions domains. It's basically a bunch of these tiny atomic pieces teaming up to create microscopic communities, and together, they possess a net magnetic moment pointing in one specific direction. They pool their individual atomic resources, basically, to create this localized collective magnetic power. It's like a tiny magnetic team working in unison.
But think about this. What happens when a piece of this material is just sitting quietly on your desk, totally unmagnetized? Well, inside, it's actually incredibly busy. There's a huge number of these domains present, but their magnetic moments are just pointing in totally random directions. You've got one neighborhood pointing left, another right, maybe one pointing up. And because they're scattered in literally every conceivable direction, they completely cancel each other's magnetic pull-out. The end result? The net magnetic moment of the entire chunk of material equals exactly 0.
So how do we get from that internal chaos to an active, working magnet? It all comes down to a crucial 3-step physical action sequence that kicks off the exact second an external magnetic force is introduced. Step 1, boom, the external field is applied. Step 2, the internal domains react immediately. They either physically orient themselves so their moments line up with the new field, or the domains that are already favorably aligned just grow in size. And step 3, thanks to this massive internal reorganization, the chaos vanishes. The material as a whole becomes strongly magnetized in the exact direction of that applied field.
Now, a super important detail here is how the material actually decides which reaction to use, and it strictly depends on just how powerful that applied external field is. If you apply a weak field, well, the material takes the path of least physical resistance. The favorable domain just increases in size, kind of swallowing up its neighbors. Actually, scratch that. Think of it more like an expanding bubble. But, and this is a big but, if you blast it with a strong field, it forces the entire structure to fall in line. The domains are literally physically forced to rotate and align themselves with that strong external force.
Now, what's really interesting about this part is how it compares to diamagnetic materials. They operate somewhat similarly at a fundamental level, but there is one absolutely critical difference. Diamagnetic substances, they're only weakly magnetized. Ferromagnetic substances, on the other hand, are strongly magnetized. That sheer overwhelming strength of the magnetization is quite literally the defining feature that sets ferromagnetic materials apart from the rest.
Let's really lock this in. We're going to summarize our micro to macro journey by rapidly recapping these fundamental physical traits straight from the source text. Number 1, put them in an external field and they are strongly magnetized in that exact direction. 2, this whole process entirely relies on the fact that a net magnetic dipole moment exists, all thanks to those unpaired atomic electrons. 3, ferromagnetism arises directly from the formation of those microscopic neighborhoods, the domains. And 4, the resulting magnetic moment is incredibly high for sure, but it strictly stays along the direction of the applied field. All right, moving beyond the shifting of domains, there's actually a crucial mathematical property regarding the material's magnetic susceptibility. While susceptibility in these materials is naturally high and positive, just look at how it relates to temperature here. It's inversely proportional to the absolute temperature minus the Curie temperature. That's the T sub C.
This brilliantly illustrates that a material's ability to be magnetized isn't just about the external field. Turn up the heat, and you fundamentally alter its magnetic state. It's a real game changer.
And speaking of mathematical rules, let's consider the number 1 for a second. In physics, 1 often serves as a baseline comparison for relative permeability. Well, for ferromagnetic materials, their relative permeability isn't just greater than 1, it is much, much greater than 1. They absolutely eclipse this single-digit baseline, which gives us yet another crazy measurable indicator of just how extreme their magnetic capabilities really are.
Finally, as we wrap up the specific properties listed in our text today, it's really worth noting the explicit categorization provided here. The source material distinctly notes that Fe, Ni, and Co, so iron, nickel, and cobalt, are listed as examples of paramagnetic materials within this specific property breakdown. We're just neutrally reporting the text exactly as it lays it out.
And that brings us to the end of our explainer. We've traveled all the way from those restless, microscopic, unpaired electrons through the formation of domain neighborhoods right up to massive, macro-level magnetic alignment. So taking what we've unpacked today, with so many subjects in the Physics Videopeath archive, what physics mystery will you unravel next? The next time you feel a magnet snap into place, remember the invisible neighborhoods working inside it. Keep your curiosity high, and I'll see you in the next explainer.